Hi everyone, today we are going to introduce quick sort algorithm to you, and we are going to use this sort method to sort this list. So we already have 10 numbers here, that is 7, 12, 5, 10, 4, 14, 6, 2, 3, and 8. So first we set the first number of our list 7 as a pivot. Then we are going to use the 2 pointers I and j to do the sort. So the list will be resulted in a low to high list. Boom! And let's begin with the j. We can find the j now is at 8, and we are going to find the j which is smaller than 7. Then let's move on to the 3. Okay, then let's find the I which should bigger than 7, then it is 12. Then let's exchange the 2 pointers numbers. Q. And let's move on from the j, and the j should also smaller than 7. Let's become 2. And we're going to find the I which is bigger than 7. Boom, 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 boom. Then it's 10. We're going to exchange them. Okay, then let's from the j again and going to find 6, which is also smaller than 7. Okay, also I, we need to find which is bigger than 7. Then it's 14. Then exchange them. Okay, now we are going to find the j, but the j meets with the I, so we are going to change the pivot and I. And j, yeah, sorry. Okay, then we find that it has already made the left part of our list, which are all smaller than 7, and the right part of the number list, which are bigger than 7. So we are going to do the recursion in our code. So let's put the 7 behind and make a quick sort here, and also make a quick sort here. Okay, then let's do another quick sort in the left part of our list. So we set the number 6 as a pivot again, and we have 2 pointers I and j. Yeah, and first we are going to find j which is smaller than 6, then it's 4. And we are going to find I which is bigger than 6. Then it's more, no. Then I meet j, then we exchange the j and pivot. Okay, we are going to do another quick sort in this list, and we have 4 as our pivot and 2 pointers I and j. From the j, we are going to find the number which is smaller than pivot 4, then it's 2. Then from the pointer I, we're going to find the number which is bigger than 4, then it's 5. Put it here and exchange the I and j. Okay, we have already found that, and for another j, we are going to find the j which is smaller than 4, but we moved here and I and j is, then j and pivot exchange. Okay, then the 5 is already put behind, and you can see the number is already sorted. Then 4, then 3, yeah, then 2. Okay, we can see the left side of our list are already sorted. Then let's move on to the right side. Okay, we have the phone numbers here, 14, 10, 12, and 8. So we are going to do quick sort here. We can find the pivot is our 14 and the 2 pointers I and j. We are going to find the j which is smaller than 14, then it is 8. And we are going to find the pointer I which is bigger than 14, yes. Then the I block meets j, and j and pivot exchanging with each other. Okay, 14 is already sorted, and we can see that the 12 sorted, 10 sorted, 8 sorted. Then the left side of our list already sorted, and we can see the whole list is already sorted. Then this is a quick sort.
Now let's talk about the time complexity of this algorithm. So we're gonna find the best time complexity of the quicksort and the what is one. So what is the quicksort algorithm? The idea of it is to find a number as a point and put it to the right place. Through this way, we just divide the whole list to be two parts, and from the left side of the number is totally smaller than the pure point, and the right side is bigger than it. So and we just do the same thing to the lesser two part of the number, and divide and divide. Finally, we just divide it to be the single numbers, and all the numbers to be sorted. So it is a quick sort algorithm. So through this way, what is the best case of it? We can find that when we set a number, for example, the 7 is a median number of the list. We will find we will find that when we put it to be the right place, it just divide the whole list to be to two smaller similar part of the list. So it is just like the binary search. So the time complexity of the divide process is log n, and we sort every numbers. So this process is O(n). So in the best case, the time complexity is n log n. So what is the case of this time complexity? It is that we set the smallest number or the biggest number to be the pure point. So when we set such a number as a pure point, we sorted it, just put it at one side. So we should sort it all the whole left numbers. We don't divide anything. So in this case, it is just like selection sort. So the time complexity is O square n. So thank you for